So let's now work on a verification. How are we going to verify our general solution? Now, to do this, it really helps to think a bit about the mathematical structure of what we are trying to solve. So let's take a look at the general mathematical structure of this time-dependent Schrödinger equation. So that we have here just up above. So it looks like this when I write it out in its full sort of traditional notation mathematical detail. And what you can see is that I have a rather complicated, although it is linear in psi, a rather complicated partial differential equation. But here's an interesting way we can think about this. What this equation is telling me is it's telling me the first time derivative of the wave function at each point x. And for each point x, I've just got a first order differential equation, and it relates the first derivative with respect to time of my function to just the value of my function at the same point times some potential function, plus then this derivative. But remember, a derivative is basically the difference between my wave function at point x and at neighboring points. So really, the right-hand side here is just some combination of my wave functions at a series of different points. And that combination with these different prefactors is telling me the first derivative of my wave function. So this partial derivative really, in a sense, looks like a set of equations for a set of variables, one variable for each point in space x, that have some coupled set of first-order differential equations. So the general mathematical structure that we have is that we have a first-order set of differential equations, diff EQs, one equation for each point x. So somewhat the way we're thinking about this is we can imagine what we are doing is we are discretizing space into a set of discrete points. And my claim is, again, if I discretize space on a super fine scale, finer than even the Planck scale from a mathematical point of view, then this derivative in x really just becomes some additions and subtractions. So what I end up with is a coupled set of differential equations, one for each point x. But now, because these are separate variables, psi, one separate variable for each point x, this partial time derivative really just becomes an ordinary time derivative, coupling the wave function at one point to these wave functions at these neighboring points. So this should bring us back then to our differential equations class, where we have that one powerful central theorem, the existence and uniqueness theorem for solutions of differential equations, and in particular for first-ordered coupled set of differential equations. And the lesson then from that fundamental theorem, which is called the existence and uniqueness theorem, is that if you have a set of initial conditions for a first-order set of differential equations, that there is just one unique existing solution to that set. And what it tells us is that we will know that we actually have the existing unique solution to that set of equations, or for us, to our time-dependent Schrödinger equation, provided we satisfy two conditions. And those two conditions that we have to check is that we have to satisfy, that's the thrust of this theorem, we need to satisfy, there's just one existing and unique solution that satisfies what are called the boundary conditions, right? And there is one boundary condition, one for each point. And it's one boundary condition because we are talking about a first order differential equation. So it's one boundary condition per point, satisfy the boundary conditions, and we have to also satisfy the differential equation, and then we've identified the unique and existing solution. So we just have to check that we've actually satisfied these two conditions. So this is what we need to verify. So we need to verify, number one, the boundary conditions, and then number two, the differential equation. So we'll start with the boundary conditions. So the boundary condition that we hope to verify is we want to take our general form for our solution, which is called psi of x and t, right? That's this complicated mathematical form that we have, right? And I want to check, actually, that if I evaluate that at time t equals 0, that the result that I get, I'm not sure, I'm putting a question mark, this is what we hope to verify, is just going to be what I started with, right? My initial wave function. Will I get my initial wave function back again when I take my general solution here and evaluate it at time t equals 0? Well, I guess technically this is my guess if you want to, be picky about it. So let's check if that works. Well, all I have to do, so this is what I'm trying to verify. I don't know if that's true, but what I know for sure is that my guess for psi of x and t has this mathematical form. So what I have then is always my sum, right? And then, as we were just saying, we've got our weights and our states, psi eta of x, and our dates, which are our complex time dependencies, which are e to the minus I. Remember, to get the frequency, it's our energy divided by h bar, and it's e to the minus I omega times time t, so I have to put time t in here. But for this part of the test, I'm just trying to see what happens at time t equals 0. So that will be time t equals 0, so I can put 0 in there. And what's beautiful about this, of course, is I'm getting e to the 0, which is just 1. So all of those terms then I can ignore. I just have a sum of weights times states, but that's very familiar to me because from the quantum principle of superposition, it says I can always find the right weights, right? I constructed those weights just so that the sum of these weights times the states would give me my initial wave function. So that sum I recognize as exactly just my initial wave function, psi naught of x. And so indeed, I've satisfied the first set of conditions, namely the boundary condition at time t equals 0. For every single point x, I satisfy those conditions. Beautiful. That was fairly straightforward. Next, of course, we need to verify whenever we solve a differential equation, we have to not only satisfy the boundary conditions, the other thing we need to check is that we satisfy the equation. So what I'm hoping then is that when I take I h bar times the time derivative of my wave function, psi of x and t, what I really hope I get back, I'm not sure yet, we will have to check, is just the Hamiltonian h operator applied to my wave function back again at the same set of positions and at that same exact time. So again, I don't know if that's true. I'm just hoping that it will be, but we can see what we actually can establish what we know. So I have to do I h bar times the time derivative of my wave function. Now let's take a look at what happens when I take that time derivative. Where's the wave function? Here he is, right? So my job now is to take the time derivative of my wave function, which is the time derivative then of this summation of these three terms. Well, I've got a time derivative of a sum, and we know that's just going to be the sum of the time derivatives. So when I take my time derivative out here, it can go then inside my sum. So I'm just going to get the sum of the time derivative of the product of these three terms. So let's write that down. I'll then have my sum then, d eta, right? Sum or integral. Then I have to take the time derivative of the product of those three terms. And let's think about those terms. So I'm taking the time derivative of these things. And I want you to notice something. These weights depend only on eta, right? That's how much of each pure state I had at the beginning. They have no dependence on time. So when I take the partial time derivative here, this I can treat as a constant and pull it out of my time derivative. So my time derivative then is just acting on these remaining pieces. When I look at this piece, notice it also has no time dependence. It has an implicit dependence on eta, which is telling me which state I'm talking about in my superposition. It depends on x because that's my wave function, that's my quantum representation of that particular pure state, but it has no reference to time. It's just a pure kinematic quantum wave function. So that also is constant with respect to time derivatives. So I can pull that constant out of my time derivative also, so that my time derivative only then has to act on this part, which definitely is time dependent. So these two are just constants I can pull out of the time derivative, and then I just have to apply my time derivative to the dates part. So let's write that down then. My weights I could factor out, my states I could factor out, phi eta of x, And I'm left then just with I h bar, excuse me, times then my time derivative. Remember, my I h bar is just a constant. I can bring that in as well. And that's multiplying then my dates, e to the minus I. My frequency is energy over h bar times time t. Okay, so now my job really is to take this time derivative. Here, I'm just going to move this here so I have a little room to write above. I think we know how to take such a time derivative. That's not too bad, right? Here, I'm going to rewrite my term here, put a little bracket. Well, the time derivative, of course, just gives me back always my complex exponential. Time derivative of an exponential gives me my exponential back. I've got my frequencies times t. But when I take that time derivative, I also bring out the corresponding factor multiplying the time, which are these pieces. So there's an extra factor of minus I e eta divided by h bar. Now this is nice because these factors here, right, that I'm replacing this term with, are then multiplied by I times h bar. So that's beautiful, right? Because then this h bar here will cancel this h bar here. I don't have to worry about that. And then I have I times minus I, which is just 1. So that's nice too. So this I will cancel this minus I. So what I've got back again is really just my energy times my my dates, right? Times my time-dependent factor. So let me rewrite this. And as I rewrite it, I want you to think about where we're trying to go here, right? We're trying to massage this thing so that we get back to the Hamiltonian acting on something. So as I write down these factors neatly, I want you to think about how I can get a Hamiltonian coming out of this. So I have phi eta of x. I had then left just my energy, E eta, which E depends on eta, and then times my time dependence, which is my frequency, E over h bar, times time t. Good. So, about things, right? We're trying to massage this thing to get some kind of Hamiltonian h hat acting in here. And if you've been paying close attention, one of the key things, and this is precisely why the time-independent Schrödinger equation is so important to this strategy, is that when we made our quantum superposition, let's see if we can find him here, our initial superposition, where did he go here? We said exactly what defines these precisely as pure states of energy is that when the energy multiplies these states, that is exactly the same thing as having the Hamiltonian acting on these states. So I can actually use this time-independent Schrödinger equation to replace E times psi with H, E acting times phi with H acting on phi. So this actually is going to equal the Hamiltonian acting on my pure state, right? Because that just gives me back again my quantum purity test. That is the time-independent Schrödinger equation that I'm using will imply that. And now you see I've got my H in here. And this is very nice, right? Because I just have a linear combination of H acting on something. But H is a linear operator. So a sum of the action of an operator is the same as the action of the operator on the sum. So in other words, I can pull this H here out of this sum, which is getting me closer to the form that I'm looking for. So I'll have H hat. And let's see what I'm left with. I'm left with the integral sum, right, of, when the H comes out, I'll have my weights still. So I'll have my weights. I will have, when I pull the H out, I still have my states. So I've got weights times states. And indeed, I still also have these factors, my dates, right? So I've just got the sum, as you can see, of the weights times the states times the dates. And hopefully we recognize exactly what this is. This is exactly our constructed guess, the thing we're trying to verify that actually solves our equation. Weights, states, and dates is just my wave function back again. So this will be psi of x and t. So all that we have at the end of the day is Hamiltonian acting on psi of x and t. Great. So now we have sort of the whole derivation here. And you can see I've gotten exactly what I wanted. So just a quick summary, what happened, I was taking a time derivative. It then can move inside my integral. And then when it sees the time-dependent part, it pulls out exactly the factor of e that I needed. Right? And then the E can combine with my states because they're pure states of energy. That's why we need this time-dependent Schrödinger equation. It's key to the whole strategy. That then turns the energy into a Hamiltonian operator, and then I can pull my Hamiltonian operator out. So I can see then I've actually verified precisely what I needed to check. So my guess wave function actually does satisfy my time-dependent Schrödinger equation. So we verified both that it satisfies the required differential equation and that our guess by construction satisfied our boundary conditions. We therefore have in this form the exact solution in the fully general case for the time-dependent Schrödinger equation. Excellent. So now what we are going to do, now that we have this beautiful solution, is we're going to run through a few examples so that I can spell out for you a step-by-step procedure for following this type of an idea to solve now for specific problems.